Hello everyone and welcome to this fourth video on quantum mechanics. This time we are going to talk about exact and numerical solutions of the time-dependent Schrodinger equation. So in the last video we have been talking about the Schrodinger equation, and we have explained that essentially it is the main equation to describe the dynamics of quantum systems or quantum objects. And this equation, in particular the time-dependent variant of this equation, looks like the one that you see here. That is a partial differential equation where we see that the partial derivative of the wave function, this psi function that you see here, with respect to time is essentially proportional to some operator, this operator h here that you see, that is applied to the same wave function. The operator h we have seen is called the Hamiltonian operator, so also the Hamiltonian of the system, and it consists in the sum of two terms. The first term being an operator that corresponds to the kinetic operator, and then a second term which is the potential term, which is essentially the terms that describe what kind of forces are involved or applied on the system. Usually these problems are presented in the context of initial conditions and boundary conditions, so also initial and boundary conditions are presented and introduced in the problem. By initial conditions, what we mean is essentially what the shape of the wave function psi is at time t equals 0. So initial conditions here might mean, okay, I have a wave function of a particular shape, and I want this wave function to be exactly the initial condition of the system. So in a way we are saying that the system is going to be set in a way where the experimental initial condition is exactly described by this function f of r that you see here. And then starting from these initial conditions, this PDE time-dependent Schrodinger equation will tell us how this function psi evolved in time. We can also introduce the concept of boundary conditions in this particular context here, where essentially we are saying what the value of the wave function is going to be on the boundaries of a certain spatial domain. So in this particular case here, if we have, let's say, a one-dimensional domain that starts at r equals 0 and ends at r equals L, so practically the range 0L, we can define the boundary condition of the wave function as being the values that this wave function has on the boundaries of the spatial domain. So in this particular case, psi at the position r equals 0 for any time is equal to psi at r equal L at any time, and this is equal to 0. This is what we call the reflective conditions. These are very well known conditions in the context of quantum mechanics. They practically describe walls that we have on the boundaries of the domain so that the particle cannot go out of the domain. So the main problem essentially becomes to find the function or the wave function which satisfies the partial differential equation represented by the time-dependent Schrodinger equation plus initial and boundary conditions if these are provided. So let's now skip to the next slide, and let's see how the whole thing works. So in particular, this is the case of an exact solution. So what we are introducing here is the case of a free particle. So imagine, for example, an electron that is in vacuum. This is a very good approximation of a free particle. So imagine that you have this particle and no potential is applied, so V of r and t is equal to 0 for any r, so at every position, and for any t, so at any time. And so in practice, this is what we call a free particle, and we say that the particle is moving in a field-free domain. We say field-free because V is identically 0 everywhere and at any time. Because we are in the absence of any applied potential, in this particular case, we can also avoid to provide boundary conditions, and we can consider the special domain as being infinite. So in this particular case, it is possible to find the exact solution of the time-dependent Schrodinger equation, which is going to be the function that you see here for a particular momentum p and for a particular energy E that is assigned to the particle. This coefficient A that you see here, this is called the amplitude of the wave function, and essentially it's a constant that is chosen in such a way that psi is a normalized function. So in this particular case, the free particle case, as we call it, is a problem that can be solved analytically, and the solution is represented by this function here. So of course I'm completely skipping the proof of why this is the solution, or how we obtain this exact solution from the time-dependent Schrodinger equation. But you might be able to take this equation here, substitute it into the Schrodinger equation, the time-dependent Schrodinger equation, and you will see that this actually represents the exact solution of the Schrodinger equation itself. So if we now go to another case, the particle in a box, as it is called, we can see that even this particular case here can be solved analytically. So what it means, a particle in a box? So this is again a free particle, so practically no potential is applied to the particle, but this is a free particle that is not now in an infinite domain, but it's a free particle in a finite domain. So this finite domain now has walls on the boundary, and these walls, you can consider them as infinite walls. So the particle is essentially isolated in this one-dimensional, in this finite domain, and cannot go out of that domain. This is represented mathematically by saying that now we have this one-dimensional potential that is applied on the system, where this potential so depends on only one component of the position, in this particular case x, and is going to be equal to 0 when we are inside the spatial domain, and it's equal to infinite when we are outside of the domain. So in practice, this infinite here is a way to say that now we have walls, we have infinite walls on the boundaries of the spatial domain. Now L, this is practically the length of the domain. So once again, the spatial domain is one-dimensional, and it is a range that goes from 0 to L. So in this particular case, again, it is possible to prove that the exact solution exists, and in this case, the exact analytical solution is represented by this function here that I am showing with the pointer of the mouse. And as you can see, in this particular case, we don't have only one exact solution, but we have an ensemble, a set of exact solutions, which are parameterized through this discrete variable here that is n, so an integer. And from this integer, essentially what you can do is you can, for every integer that you have, so n equal 1, 2, and so on, you can define every time a new kn. This kn is also called the wave number of the particle, and you can also define a new energy that is defined in terms of a frequency that depends on this integer n. So every time you introduce an integer n, which can be 1, 2, 3, and so on, essentially you can define a new exact solution of the Schrodinger equation. So in the case of the particle in a box, not only we can find the exact solution analytically, but we find an ensemble or a set of these exact solutions. Again, in this particular case here, I am completely skipping the demonstration or how we got to this solution. But if you are interested, you can actually show that this is an analytical solution of the Schrodinger equation. You just have to substitute it in the Schrodinger equation wherever you find the wave function. You will see that this satisfies the time-dependent Schrodinger equation. So we can now go to the case where we don't really know how to solve the Schrodinger equation in an exact way. And this is what I would say the commonplace if you are a practitioner in quantum mechanics or in applied quantum mechanics. The usual case is that you cannot find exact solution of the Schrodinger equation. And this is due to the fact that the potential is not going to be a very nice and smooth function, and usually in applied cases it can be anything. So a general analytical way to find the exact solution is completely out of the equation. But there are ways to find approximated solution of the Schrodinger equation, and this is what we are going to introduce here. So numerical differentiations. So numerical differentiation is a term to say something that is actually very simple to understand. In many of these equations we find derivatives. So what we are going to introduce here is an approximations to derivative, a numerical approximation to find derivatives without actually having to apply the analytical definition of a derivative. So in particular, when we are in a situation where exact solutions cannot be found, the very first thing that we have to introduce is the concept of grids and discrete variables. So if we are in the presence specifically of a one-dimensional domain, this means that we are going to have to introduce a grid in space, which is what is represented here, that goes from 1 to m. So here we have a certain number of cells that are now covering this one-dimensional space here. And in this particular case here, the space has been divided in equally in equivalent cells that have the same length. The length here is represented by delta x. So this is the simplest case to introduce a grid. You might think of heterogeneous grids where delta x can change position after position or cell after cell. This is the simplest case that we can think of, and this is the case that we are going to use to introduce numerical differentiation that we are going to see in the next slides. In the very same way, we have to bear in mind that space is also a one-dimensional variable, so it has to be discretized as exactly it has been done for the spatial variable. So in this particular case, if the time ranges, let's say, from 0 to a particular final time tf, then this final time tf will be divided in a certain number of time steps that will be now indicated by this time step here, delta t. So we will improve every time we will move in time steps equal to delta t, and we will use spatial grids where the cell has a length that is equal to delta x. So if we are now in this context of discrete variables and grids, we can now introduce the concept of finite differences that actually come from the concept or the very definition of derivative that you see at the bottom right of this slide here. So what is a finite difference at this point, and what is the finite difference method? So a finite difference is essentially a mathematical expression of the type that you see here. So for example, f of x plus b minus f of x plus a. So you have a function f that is a function depending on one variable, and you are introducing now an interval in this variable. You are introducing 2 points, and the points are x plus b and x plus a, and what you are trying to do is the finite difference is essentially the difference of the values that the function has on these 2 points. So while this might sound like a very simplistic concept, this is of very big importance. This is of fundamental importance to approximate derivatives, as we are going to see. As a matter of fact, finite difference is very important, so important that it can be the basis of what we call the finite difference method. And finite differences are utilized nowadays on a regular basis, actually, to integrate ordinary differential equations, so ODEs, but also partial differential equations, PDEs. So all of this, it's a numerical way to approach this equation and to find these equations and to find, let's say, an approximated solution. We have three basic types of finite differences, which are reported here. So we have forward finite differences, which are of the type f of x plus h minus f of x. We have backward finite differences, which are of the type f of x minus f of x minus h. And then you have the central finite differences, which are essentially of the type f of x plus h over 2 minus f of x minus h over 2. And these three types of finite differences are utilized to introduce the concept of approximation of a derivative. So in particular, in this case here, I'm showing two different ways to use finite differences and to approximate the first derivative of a function and the second derivative of a function. So in here, you clearly see that there is one kind of finite difference. This is the forward finite difference. While here, if you look closer, you will see that there are two kinds of finite differences. And in here, we have the forward and the backward. And I am leaving it as an exercise for whoever is interested. So now we know what a finite difference is. We know what finite difference method is. And we know how to approximate derivatives by using finite differences. So we can now introduce the method of Euler, or the Euler method, which is a method, or let's say, which is a first-order numerical procedure to solve the ordinary differential equations or partial differential equations, provided that we have, of course, initial and boundary conditions. This is one of the simplest and most basic explicit method for numerical integration, but we are lucky because it turns out that this method is very robust and very stable if applied to the time-dependent Schrodinger equation. This is not always the case. For example, if you apply the Euler method for certain kind of equations coming from the field of fluid dynamics, you might be surprised and see that actually the Euler method doesn't work in these cases. They might introduce spurious oscillations or provide too poorly approximated solutions and so on. But the Euler method works like a charm when it is applied for the Schrodinger equation, so this is what we are going to use. How do we obtain the Euler method? This is pretty simple. We use the finite difference, forward finite difference approximation for the derivative. So in this particular case here, this would be the approximation, while in here this y prime, what I mean by y prime here is the derivative with respect to time of y, so it's the time derivative of y. And the way we approximated it is through this approximation here, where you notice that the variable that we are using here is the time variable. So this would be the approximation for the time derivative. And if we use this approximation in the original equation for the Schrodinger, let's say, for example, in an equation of this kind here, so y prime equals some function of some function f of t and y, I mean, what you will end up having the following numerical method here. And this is what we are going to apply to the Schrodinger equation. You can write the Schrodinger equation in a shape that looks like this equation here. So eventually you can use this numerical method to numerically integrate the time-dependent Schrodinger equation and find the time-dependent approximated solutions. So if we apply now the Euler method to the Schrodinger equation explicitly, this is what we obtain. So we have introduced a discrete time, we have introduced now a discrete space, so we have agreed for the time variable and we have agreed for the space variable, and we apply the Euler method that we have just seen in the previous slide to essentially approximate the time-dependent variable. In the same way, we use finite differences that we have seen before to also approximate the special second derivative of psi that you see here, and essentially we end up having a way to numerically discretize the Schrodinger equation. This will be in practice the Euler method that we are going to use and apply on the Schrodinger equation. This is going to represent the rule to update the wave function at every time step and for every cell of the grid. So when we report here n, we mean the discrete variable which represent the time steps. So here n would be the solution psi at the time step corresponding to n, and here you would have the solution psi corresponding at the time step n plus 1. So, and in the same way, when we take the variable I, this is a discrete variable and it is used in exactly the same way as for the time variable n. So now we can go into more details and we can start to tackle the simulation of the quantum tunneling of let's say a particle. So we imagine that we have some quantum particle that is in the proximity of some barrier, and we would like to simulate the tunneling through the barrier of the particle. So the initial conditions in this particular case, we are going to use initial conditions that are pretty simple, and we are going to use the Gaussian wave packet in particular, which looks like these two exponential that are multiplied with an amplitude. So amplitude, once again, this is going to be a constant that we use to normalize the wave function. Then we will be in the presence of boundary conditions. In this case, we will use reflective boundary conditions. So we imagine that the wave function cannot go out of the spatial domain, and that the spatial domain is a range that goes from 0 to L, and that the wave function is 0, identically 0 on the boundaries of this domain. For the discretization, we are introducing a one-dimensional grid for the space, and which consists of nx cells. And for the time variable, we are going to introduce a time step, which we will call dt or delta t. And the update rules, of course, will be the Euler method that we have just seen. So if we now apply this, we can obtain a pseudocode like the one you are seeing here. And in particular, I mean, in this pseudocode, there are a few things that I would like to highlight. The first one is that, as you see here, somewhere in the code we are going to define what is the final time that we want to have as the final time of the simulation, and we are going to divide this final time by a certain number, an integer nt. This is going to provide us the delta t, or the time step of the simulation. In the very same way, I mean, if we are in the presence of the spatial grid, it's going to be the same. So now L is the bigger, or let's say it's the length of the spatial domain, and you're divided it by nx, which is the number of cells that you have in the grid. And by doing this operation, you obtain now the length of the cell that we call dx. And what you see here is now, if we apply the Euler method is going to practically consist in this main nested loop that you see here. The first for loop that you see is a loop over the time step, so it will go from 0 to nt, or equivalent, well, in this particular case we are using the C language or something that is close to the C language, so it goes from 0 to nt minus 1, but you might also run this loop from 1 to nt equivalently. It wouldn't modify anything. And for every time step that you are going to run in this loop here, you will have every time to apply the reflective boundary conditions. So these are the boundary conditions we apply. And as you can see now, psi on the cell 0 is equal to 0, and psi on the cell nx is equal to 0. So that's the what we do to apply these reflective boundary conditions. In here, just to know at what time we are calculating the next solution, we can update the current time, and then in here we have the main step, which consists in updating the wave function. So in here you see clearly that there is another for loop that ranges now over the cells of the special grid, so from 1 to nx. And what we do every time is that we are going to update the wave function psi on the ith cell of the special grid, and the way we are going to do this is by applying this formula here that essentially represent the Euler method. There is one trick that we don't see here in the pseudocode though, and this is something that I will leave as an exercise to whoever is interested. This pseudocode here as something that is missing, and what is missing actually is that we are updating the function psi using the same array in various position, but this would mean that essentially as soon as we have updated a few of these numbers here, we are going to have a mismatch between what psi is in the previous time and what the value of psi is now at the current time. So in practice, what should have been done before this update of the wave function is that the wave function itself should have been saved somewhere. So we should have stored the previous value of the wave function in another array, and then use this other array in this right hand side here of the equation here, so that now there is no overlap between the old values of the wave function and the current values of the wave function. So I will leave this as an exercise, and now we will see what happens if you apply the Euler method implemented for the time-dependent Schrodinger equation. So in this particular case here, what we have run is a wave function that is impinging towards a barrier. The barrier is represented by this red line that you see here. So there is practically nothing on the totality of the spatial domain, with the exception of this very small area here where we have a barrier. And we start from a wave packet that is somewhere localized here and that has a direction that goes from left to right. So the wave packet is moving towards the barrier. After 20 femtoseconds, so after running the Euler method and reaching 20 femtoseconds as final time, what we observe is that now the wave function doesn't really look like the Gaussian that it was at the beginning, but it has one peak here, and there is a little bit of tunneling through the barrier here. So things are happening, and the wave packet is evolving in time. If we continue, if we let the simulation continue and we go to time equal to 40 femtoseconds, so we now double the final time, that's the situation that we will find. This is the solution that we will get. So now we have 3 peaks here on the left hand side of the barrier, but we have a prominent tunneling happening through the barrier, but also on the right hand side of the barrier. So practically what this simulation has told us is that even though the particle is completely localized on the left hand side of the barrier at time 0, it can be found and it can be localized after 30 femtoseconds on the right hand side of the barrier. So there is a possibility, there are probabilities that the particles tunnel through the barrier, which is something that we were expecting if the simulation was correct. This concludes this video. I thank you very much for your attention.